סוג של תקצר את הסיפור של Deep Learning, עם זה יש התענות שכל מה שצריך לעשות, זה לקחת המון דאטה. מה? English?
English, yeah, can you do it in English? Oh,
yes, of course, no problem.
Thank you.
So, some might say that the story of deep learning is if you have enough data and you have enough compute resources, then that alone is enough to get amazing results. And this is somehow supported by data that there's been like a phase change ever since 2012 with the internet moment, where using neural networks, people were able to beat the then state-of-the-art result on image recognition, or the imagery challenge. And ever since, there's been this drive to train ever larger neural network models using more and more data. And in conjunction with this trend of using larger and larger models, in part of that there's also been dramatic improvements across a lot of benchmarks in vision, in speech, in language. So across many different tasks, we see a dramatic improvement in the accuracy. I mean, it's to such an extent that it's sometimes hard to tell if a new method is better than an old method, or they simply they had more resources, more computational resources at the time. So it's but you actually know that even if you normalize whatever training method or model you use, and you just measure the performance as you spend more computational resources during training, even if you control for that, you see that as you spend more computational resources to the problem, you can actually get better results. So the standards support this recipe for success. But this is this trend, this recipe is both a blessing and a curse. Because on one hand, by trying to work with larger and larger models, like you actually get these amazing breakthrough results across the various domains, from image recognition, mastering the game of Go, and most recently the innovation of ChatGPT. But all these results don't come for free. There are actually there's a large practical cost to using these large models. So to begin with, just training these models takes massive capital. It can be as large as more than $1 million to train a single model, which more or less means that only the largest companies in the world can actually train these models. Additionally, even if you have the monetary resources to train these models, it takes many months, which means you have to do a lot of planning ahead of time to make sure that the architecture is right, the data you train on is right, because once you begin training, you're going to make small adjustments. And finally, even if you are able to have access to one of these very large models, local inference is often impractical, either on consumer-grade GPUs or just CPUs or even mobile phones. If you want to use these kind of large models, you have to try to compress them, and in doing so, it often leads to diminished performances. So there are all these practical costs with using these very large models, but there's also this ideological view that I have that trying to build larger and larger models cannot be our answer to building intelligent machines. It doesn't seem like a very intelligent thing to do. So these are my two motivations for trying to see how can we make these models more efficient. Well, from a practical perspective, we want to lower the cost, and from a ideological perspective, there must be a better way for training and using these models. So I want to emphasize that I'm not against I'm not strictly against this chase for larger modules and through that getting better results. But this is a game mostly for the larger companies in the industry. So what I'm trying to do in my academic work is try to go in the other direction, try to reduce the cost per performance, so try to stay at the same level of performance, but reduce the cost. And in my various works over the years, when I've looked at this problem on different domains, from vision, natural language, and even quantum physics, I can kind of divide my works into two parts. There's this theoretical part, where I'm trying to understand how current methods scale, and in doing so, to provide some guidance into how to pick the optimal configuration for a given model architecture. And there's this practical side of trying to actually develop new approaches to get a more efficient inference. So let's start with the theoretical side. Where, as I said, we're trying to understand from a theoretical point of view how different architectural choices affect this scaling, and I'm focusing specifically on the expressivity of the models, meaning how large does the model needs to get to be able to represent certain functions. And here we are studying this widely known result where apparently all neural networks are equally capable, right? If you, we all know that as you increase the number of parameters, and it doesn't really matter what kind of neural network architecture you're using, you will be able to approximate any continuous function. So our deep learning architectures are really all equally capable? Of course not. It's just simply that parameter count is a very crude metric to look at. We need to look at more granular architectural choices, such as looking at comparing different depths of models, or if you look at convolutional networks, look at the receptive fields, or even comparing two different architectures, and so on. And each of these choices, if you have no theoretical background, that just increases the high parameter set space, which grows combinatorically. So developing a theory to guide your search for in architecture space could really improve your overall training cost. And I'm going to talk about, before I'm going to get to the actual results, I'm going to first give two high-level ideas that share between all these works. So the first high-level idea is the use of something called the separation rank as this complexity metric to try to assess how complex is a certain class of functions to be presented by a neural network. So what is the separation rank? So given some function y over n variables, we're going to pick some partition of the variables into sets. Like on the left, you see this interleave pattern. On the right, you see this splitting all the variables to the left and right side. And then the separation is defined as the minimum number of separable functions equal to the original function. So what do I mean exactly? So let's say the separation rank is R. That means there exist RG functions that operate only on the variables in set A, and RH functions that operate only on the variables in set B. And then there is an equality between the function and the sum over the product of these two functions. So that's the definition. You can maybe kind of see why it's called separation rank, because It's kind of similar definition to the matrix rank, because it is the sum of rank 1 matrices. But also, there's also this interpretation you can make that can relate to more practical, to how it relates to practical problems. Specifically, the separation rank can think of it as a proxy to how much dependencies exist between the two set of variables induced by the function. So if the function is a probability density, then this matrix this interpretation is exact, meaning that a rank 1 function, a rank 1 separable function is literally the probability density over two independent set of variables. And as the separation increases, this increases the distance from these two independent sets. The second idea is mapping neural networks to arithmetic circuits. So first of all, what are arithmetic circuits? There are simply circuits composed of two kinds of gates, a product gate and a weighted sum gate. And the reason they're interesting is that they're essentially polynomials, which means we can analyze the separation rank using algebraic rank-based methods. And the transition from neural networks to arithmetic circuits is actually a very simple change, relatively speaking. Usually it simply entails changing the activation function to be either linear or multilinear or some polynomial, and then you get an arithmetic circuit. And to give you two quick examples, so in our original paper for 2016 with Nadav Cohen, we showed that a convolutional network composed of a radio activation and average pooling can turn into an arithmetic circuit, but by switching the radio activation to linear activation and the average pooling to product pooling. More recently, in 2020, in the work with Yoav Levin and Noah Weiss, we're looking at self-attention networks, and their change is switching the softmax normalization, the attention layer, again, to a linear function. More recently, I actually figured out that the other mapping is also true. So actually, any arithmetic circuit is already a neural network if you examine it by taking the log of the arithmetic circuit. So the log of any arithmetic circuit with non-negative parameters is exactly, no approximations, a neural network with what's known as the soft plus activation function. Okay, so these are the two. Yes, sorry.
Question: how does it work when the network is not a simple feed-forward network? When it's a feed-forward, so I can imagine. Okay, say this layer is this action, but once things start to become sort of circular, how
what do you mean by circular?
Recurrent or GMMs, right?
You simply unravel it through time, right? And then you get a specific function. I mean, this work is using some function. So if you want to unroll the component, then you work on that. Same with like other types of like recurrent-like networks. So using these two ideas, you can now apply these sort of techniques to analyze different architectures and ask different questions. Let me give first like a very simplified example. So here's a way to represent a shallow convolutional network where it composes of like these two layers. So we first take a one-by-one convolutional window over the inputs, and then you use a global product pooling. So if it was a standard relay network, you apply a value activation up to this step, and then use average pooling. So this is the mapping that I mentioned in the previous slide. And we can represent this network very simply using this simple equation. Like this is like the sum, product sum structure that it has. So this is really just a polynomial function. And now, if you want to find an upper bound on the separation rank of this function, then it's very simple, because for any partition of the variables, because each of these sums operate over a single variable in the input, in just a product of these simple functions, you simply divide the products according to the two sets, and you get these, and just shuffling the terms, you get this product of these two functions, where here's all the products for this belong to the set A, and here are all the products belong to the set B, which means you already get this expression corresponding to the separation rank definition, where these two functions are the H and the G functions from before, which means that the separation rank can be at most R, where R is the number of channels you have in the network. Yes?
How is the separation rank even computable?
What do you mean computable?
It seems that it's almost impossible to guess what R is.
To guess, this is defined by the architecture. R is the number of channels. It's down from here.
Right.
These are the number of channels you have in the convolutional network, which ultimately correspond to the number of parameters that you have in your model.
But what guarantees that it represents indeed the separation rank, for example, of the function of the neural network?
Okay, so the separation rank, this is a property of any function. And here we're trying to find an upper bound of this property. Like the matrix rank is a property of any matrix. So this is literally the definition of the neural network. This is the function. Here I'm showing you by simply shuffling around the terms. I'm not changing the function, that's changing the order of the products. I'm already putting in the form of the separation rank definition.
But what if the net has a representation that is much more simple, because many times some weights cancel themselves, and then
Again, this is an upper bound. This is an upper bound. It's not as, I mean, if all the weights are zero, then you get a zero function. It's going to be a zero rank. Yes, this is an upper bound, not exact. Yeah. And because what I'm driving, I'm trying to show a separation. So I'm trying to find an upper bound on the shallow networks, and next I'm going to show you for the deep ones, for the deep networks, in a lower bound. And that's where you get separation. So next, let's just do like one step deeper, just another set of layers. So just this, like before, when I did another set of one-line convolution, followed by this time product putting but on a smaller window, like a 1 by 2 window, effectively, which gives you this slightly more intricate, but not that more intricate expression. So now we want to find a lower bound for the separation for this specific function. And now before you could look at any kind of partition, now we look at a specific one, which is the interleaved partition from before. It's like checker mark pattern. So the first step is we want to move from operating over functions to operating over algebraic expressions. So the first step is we're going to discretize the function, and using that define a tensor. So what it means, for each of the input variables, the x's, we're going to limit it to a finite set of values with z's, 1 through d. Next, we're going to find this tensor with high-dimensional array, where it has n indexes, 1 for each input variable, where the index picks for each variable which of these predefined values it uses. It's just a discretization of the function. You can control how fine discretization is. Next, we're going to take this tensor and metricize it. Meaning we're going to simply reshape it such that all the rows correspond to the indexes in the set A, and all the columns correspond to the indexes in set B. And finally, a claim, the rank of this matrix is a lower bound for the separation rank of the function. And you can see that if you look at the separation rank under this discretization, you literally get the definition for the matrix rank as the sum of these rank 1 matrices. So this is why you get this lower bound using the matrix. And finally, we simply need to find some assignment for the parameters to maximize this rank. And specifically using this simple assignment, we can show that this matrix will be equal to this quantum product of almost identity matrices. We have ones and then zeros on the main diagonal. You have especially R ones and then the rest zeros on the main diagonal. And then the rank of the product of the quantum product matrices equals to the product of the ranks, which gives you this value. So the rank of this matrix of this discretized grid tensor equal to the minimum between R, again, the number of channels, D, the number of values of discretization, to the power of n over 2. Which means that with even a depth 2 network, you can already realize this exponential in the input length separation rank, which means that you can get this separation between depth 1 and depth 2 network. So this was like, even if you have questions, ask now, because then we'll move on. Okay. So this was like a simplified version of what we showed up in our first paper on this subject, where you show that the deep networks are more expressive than shallow ones, because they can represent separation ranks that are far larger than shallow ones. And if you want to look at the same functions of these high separation rank using shallow networks, they will have to use an exponential number of parameters in the input length. Yes.
Can you generate a network that attains the upper bound?
Yeah, yes, this is exact. You mean for the shallow network or?
Both.
Yes, so here I'm literally giving you a specific assignment for the parameters. So these A's are like the parameters, like the weights and of the convolution layers. So these are the specific parameters that like maximize the separation rank. Yes.
What is the connection again between the separable rank and the complexity of the, or the, not complexity, like...
So think of it as, like, if you look at the space of all function, like slicing it to different parts. Where the separation is lower, there are slightly simpler functions, right? Okay, think of it kind of like the analogy to matrices, right? Rank 1 matrices are simpler. You use fewer parameters to represent the matrix. As the rank is larger, you need more parameters to represent the same function. So that's like the analogy here. And also give like this intuition, this relation to how like the dependencies induced by the function. So a function that can present more intricate dependencies between different pixels, like in the image domain, this interleaved partition, think of it as capturing the idea of local dependencies, right? Because you think that the nearby pixels should be highly dependent, but far away ones less so, like journalists.
I'm not sure I understand the notion of simplicity here. Isn't it also true that a wide, shallow network can represent functions that a deep network cannot?
Yes, but the point is under what parameter budget you're using, right?
No, but let's just make it very concrete. I have 1,000 hidden units, so my width is 1,000, and then I have a depth 5 with width 4. Clearly, the one with 1,000, the shallow one with 1,000 can represent something that the deep one cannot. It's just a different class of functions. You want to argue, isn't that right?
So
Why
not quite, right? Because I mean, because I'm trying to like simplify like the interaction, but one of the steps that I've skipped over is that with a a small increase now parameters of the deep one, you can represent the same function as the shallow one. So, for instance, in the increase from 4 to 1,000, I mean, like in absolute values, that's a lot, but in asymptotic terms, it's a factor, right?
Let me give you an example. If the depth is 1, if the width is 1,
Yes.
then no matter how deep you are, there are a lot of functions
Yeah,
you cannot represent.
So let me rephrase like the claim here. It's more about like the asymptotic behavior, right? How quickly does the network is to grow to be able to build a sort of class of functions, right? So in the shallow case, as you have a network with 1,000 layers, you only need to increase the deep network to 1,000 channels. So the number of ones that didn't increase exponentially, but in the other way around, the channel will need to increase in width to an exponential in the number of inputs. That's the difference, right? How quickly do they reach the same? How quickly they can represent the same set of functions?
But also, you're not claiming that you can represent every function of some complexity with this new network. Right?
Sorry.
You're not claiming that you can represent every function with some.
No. I'm claiming that the depth to convolutional network can represent some functions in this from this space of high separable rank functions. Not all of them, of course. So now we quickly walk with you through some results. So this was the first one. We just showed up the depth separation between shallow and deep. The next one is interesting because it's completely orthogonal to the depth versus shallow perspective, more commonly been studied in the past. So here I've looked at the receptive fields in convolutional networks, and specifically the relation between the size of the receptive field and stride. So when you have a convolutional network, you can either have all the convolutional windows like densely packed, or you can use like some jumps in between. And here what I found is that if you look at the most extreme case, where you have completely non-overlapping windows, versus the case you have some amount of overlap, even a small one, and again you have this exponential separation between these two classes. Which is again completely orthogonal to depth versus width. I mean, you can have like a shallow network with overlaps, which will beat a deep network without overlaps. But up until this point, I'm kind of like explaining things like in retrospect. I mean, everyone using convolutional with overlaps, everyone did use deep networks.
Not transformers.
I mean, that's what I guess. Mostly have the most overlaps. But now I'm going to switch to something slightly different. So one of the things you can look at is trying to examine networks that are expressing for achieving a specific task. So in this case, I've looked at the ability to represent wave functions in quantum things. So about 7 years ago, physicists have begun replacing an element in their numerical simulations with neural networks. And specifically, one of the things physicists are after is trying to find the wave function of a given physical system. I'm not going to get into too much what is a wave function, but it's simply the object that captures all the information for the system. So you think in a classical physical sense, the state of a system is like where are all the particles allocated in space and the speed. In quantum physics, you get this like distribution over where they can be, distribution over their speeds. So the state of a system is not a point in space, it's a function. And for some of these complex systems, you can't represent these functions analytically. You have to use numerical simulations to try to find an approximation for them. and physicists have begun using neural networks as an approximate. And initially they were using very simple networks like RBMs. And what we at the time were looking at is trying to...
I don't think anyone knows what an RBM is here.
It's like don't think of it as a shallow one hidden network with fully connected network with a single layer. Anyhow, we at the time were thinking, okay, so do different network architectures are more well suited to the task or not? So, and one of the things we found out was that our definition for separation rank just happens to be almost the exact definition that physicists have used to define the entanglement of the system. And entanglement, again, simplifying, you can think of it again as this kind of measure of how two particles are dependent or correlated with each other, which happens to have almost exactly the same expression as a separation rank.
How, in the sense of to what extent or how many? Like if I think of it as a graph, so it's how many edges I have, or what's the average weight of the
it's more like the weight, right? It's not not interacting, it's like the how much. Again, I don't have the time to get into the details of exactly how it's defined, but it's almost exactly what I just how it's kind of separation rank. And with that, it allows us to, again, look at different class of functions and figure out, okay, for this specific goal, which class of network architectures are able to express highly entangled systems. And here we have this result that shows that convolutional networks can more efficiently represent highly entangled quantum states than the coordinate networks, which at the time they were one of the two new architectures that physicists have begun to use. A bit more recently, and that's like the last, next to last theoretical work, I've actually shown that deep networks are, in many ways, are strictly more expressive than almost all prior models that just have used to model the wave function. It's a large class of analytic of functions called tensor networks. And finally, the last theoretical slide. Again, up to now, all these different works have used like these same two principles, right? So these two principles have been applied to a wide range of works. And then the last one, again, it's a work with Yoav Levin and Noah Weiss, where we looked at transformers, self-attention networks, and looked at specifically the relation between the depth and the width of the network. And specifically, we found that you have to increase it both in tandem if you want to maximize the expressivity of the network with respect to the number of parameters. More interestingly, what we find is that most architectures that people have used trained at the time were either too shallow or too deep, including like in the far right, GPT-3. And now I want to make this switch to the more practical side of things. So, 3 years ago, I was working for AI21 Labs, and at the time we were trying to build our GPT-3 competitor. So, of course, as I said at the very beginning, I mean, it takes a lot of resources to train these models. You have to plan ahead. So, in an effort to reduce the risk of training these models, based on this theoretical work, we've picked the architecture of the model exactly precise to our predictions, which means using a slightly shallower network and slightly wider network.
Sorry, I missed. How is this curve related to the rank separation? And
Okay, so This curve, this is an empirical fit based on how we expect the relationship to be. So we've trained a bunch of networks. Like so these are these smaller x's here, but more than these 5 dots, and fitted the graph according to the prediction. Obviously, in the theoretical side, it's not exactly central. So we switch the softmax to linear activation, and obviously there are hidden constants in all expressions. So we had to make this empirical fitting, and then we extrapolate it to larger size. So when it came time for me to actually train this very large model, that's one of the decisions we made. Yes.
How do you measure here the depth? Like in the total number of parameters?
The depth is the number.
No, not the depth. The width. Sorry.
The width. So he is actually the network size. So it's not total parameters, but you have a separate graph like, with the width. The width of the transformer is like the number of hidden. And it's called the hidden size. How many coordinates you have for each word in there.
Yeah, I see. Okay, thank you.
What is transition?
It's the point in which exactly the trade-off between if it's too deep or too shallow, like the optimal growth rate.
So you have some accuracy measure or something like this after you train the
Yeah,
network?
specifically here is based on perplexity, like how well it's generalized to the validation set. All these small networks will train them. So this is like the end of the theoretical part, and I'm switching to the practical side. So having a network that's slightly shallower or slightly wider actually has some practical benefits beyond the expressivity performance. So if you think about it, a deep network is like a single thread. As you have a wide network, you can compute it with like multiple threads in parallel. So using wider networks, you can actually improve the inference speed as you generate a text using these large models, right? And so by simply switching to this slightly shallow network, we were able to improve the text generation speed by 23%. By simply doing this trade, while keeping the same accuracy metrics on a large set of zero-shot metrics. The other thing that we did, not only connected to the depth-width trade-off, is that we made some domain-specific optimization. So, like the theoretical work about transformers, that's general. It doesn't have any kind of domain-specific knowledge. It's true for visions as it's true for language. But for language, you cannot look at just at the network as a network. You have to think of what's the input of the network. And the input to transformers, the way you input text to it, is by first tokenizing the text, which means divide the text into smaller chunks and map it into some fixed vocabulary. So, for instance, if you look at the United States, you can tokenize it like character by character, or as United and States, or as like this large multi-word token United States. So all three are technically possible, and there are different works that takes different ways to tokenization. And we specifically made a few changes to what people commonly did at the time. So first of all, we used a much larger vocabulary. We use 256,000 words and tokens in our vocabulary, as opposed to just 50,000 in GPT-3. We also use multi-word expressions like United States. And with many other smaller tweaks to how we tokenize and what words are in or not in our vocabulary. And on average, we're able to present about 20, using using 28 fewer tokens, we can represent the same text. So it essentially means that our transformer model, using fewer tokens, see more text. But as it uses fewer tokens, it sees the same set of text, which means that, again, it is translate to faster text generation, right? Each token we are producing encompasses more part of the text. So combining both the depth optimization and the vocabulary optimization together gets it to up to 80% more efficient, faster text generation, using both the theoretical insights and these domain-specific optimizations. Okay, never mind. And last, I'm going to the last part of the talk. Yes, sorry, yes.
Okay, you determine the optimal width empirically, right? You don't have your theory doesn't let you, or does your theory?
It gives you an asymptotic growth.
Yes.
But
how do you get to that particular sizes that actually achieve that same?
By empirically testing on a large set of small networks and then projecting according to the asymptotic growth. So we fit.
The result is shown as that based on that projection. That
This graph, yes, that's an empirical graph where like the functions don't fit into the data. That's based on the theory, but all the constants are different. They are fitted to the specific case.
And do you know if this graph depends on which data set you train?
We use just a standard data set from Wikipedia and the book corpus, I think, at the time.
I guess I'm wondering between vision and text, let's say, do you get different curves or do you get the same curve?
I mean, I would expect that, yes, it would probably make a difference, right? Especially vision versus language would probably slightly different scale. The asymptotic growth should be the same. That's on the theory side. But the constants can be different, like widely, right? Though we haven't, I personally haven't tried specifically for vision, so I'm not sure how it looks like exactly. And finally, so the last part of the talk, like my most recent work, is about improving the inference speed using a completely different method than what people have been doing up to now. So usually, if you are given a model and you try to make it run a bit faster, after you pick the architecture and everything, that typically means you try to compress the model in some sense, right? You're using quantization techniques, pruning, and other methods to compress it. And in doing so, usually you lose some of the abilities of the model. Here in this work, I'm doing something slightly different. Instead of trying to compress the model, I'm actually going to compress the computational graph of the model across different inputs. This is in the setting where the model doesn't operate over this random different inputs of the model, but we're looking at a given input and it changes over time. So two examples where this is relevant. So one, think of AI writing assistants, where you have some document that the user edits all the time. And after every edit, you want to update the writing assistant suggestions immediately. Another completely different case, again, is the quantum physics labs, where in some of these numerical simulations, that we use neural networks as a way to represent the wave function. So one part of this numerical simulation is looking at these perturbations of the particles. So again, you have this where I should explain that the input to the neural network in that case is like the configuration of all the particles, and then you can slightly perturb them. And again, try to complete the function over all these different perturbations. So in both these cases, we are applying this technique. You can achieve significant speed-ups by not trying to compress the network, but trying to reuse different parts of the calculations. So let's start again with the writing assistant example, which is more relevant, I guess, to most of you. So as I said, the idea is that you have a document that you edit, the user edits all the time. Like in this case, changing the large to small. And so typically, the way people commonly address this problem is you read the first document, you upload a prediction, and then there's a new revision, you throw everything away and you start from scratch each time. That's the current method, which as you assume is very costly. And what we're trying to do is trying to reuse all the calculations we made before and just update the results instead of starting from scratch each time. And like in the wider science world, that's called incremental computing, right? If you have this graph of dependent tasks and some small part of the graph change, you only need to recompute the entire graph, only the subset of the graph that has been affected. Like when you try to recompile your source code and you change a single file, you don't recompile the entire project, only the file that was changed and those that are dependent on it. And we try to essentially apply the same idea, but for neural networks. But when you come to apply this idea to neural networks, you encounter the following problem, where neural networks, because they are based on these continuous operations, and they are very connected, if you change just a single input, it will impact almost all the neurons in the graph. Maybe by a small amount, but it will have some impact. And that's true for fully connected networks. It's true for convolutional networks, where like in the beginning the effect is small because they are local operations, but with every new layer, the effect grows and grows. And that's even true for autoregressive networks like RNN transformers. So in some sense, if we think of autoregressive networks, networks that are optimized for a specific kind of incremental update. That is when you append something to the end of the list, right? Because they are constructed in such a way where each input is only connected to what came before, but what came after. So if you change an input in the middle of the network, you only need to update everything that comes afterwards. So if the only kind of changes we make are appending something to the end, yeah, that's very efficient. That's why text generation is efficient with transformers. But if you are trying to update a document and make a change anywhere, they are very inefficient. So here you have the immediate thing you might want to do is let's just try to limit the connectivity of the network. In doing so, constrain the effect that changing is a local change on the other intermediate values. But as we kind of seen before, like again, kind of like this summary of mathematical works is that in many sense this highly dense connectivity, because with the neural networks, is kind of like the source of why they are so expressively efficient. So we don't really want to limit the connectivity. We want to find some other way around the problem.
Doesn't quantization maybe even exponentially simplify this?
That's a good insight. We'll get to that. That's one option. So first of all, it's an observation. So if you look at the transformer network, you actually make this kind of change. So this is a paragraph taken from the squad dataset where you have some background paragraph and a question on the paragraph, and I've changed one word. So in this paragraph, it's about the Apollo 8 crew, and they've taken the book of Genesis to the moon. So I've changed the word Genesis to numbers, and this is critical because that's not the question you ask. The question is, from what Bible book the Apollo 8 read? So by making this change, this is like the most important part of this paragraph related to this question. And this is what you see in this graph. You see like for different layers, this is like different token positions, and you see by how much did activation work changed. So you see that like near the change, like before the change there's no difference because these networks are autoregressive. At the change, there's like a lot of difference, but as you go away from the token that was changed, in most of the network, there's very little change. Most of the network stays almost the same. You see that very near the end, there's another peak. because that's where the answer is, which looks at what was changed, and that's what gives you that. So you see that most of the activation map is actually very sparse if you look at the difference. So we want to build on all of that. So essentially the idea is you get efficiency by resisting this change. And there are different ways to do that. One is actually quantization, but that's like related to another work. Here I'm offering like an even simple solution. By using a simple heuristic that you simply going to roll back any change that less than some epsilon that you choose, like 0.1. In doing so, if you just add this like a step after you have a neuron, then after this step you going to roll back any difference that's less than epsilon, and you plug that back into the network. Now, when you make a change, then in some cases, it won't affect the network. It acts as some kind of filter inside the network. Okay, so how does that help us? So obviously now some large part of the networks is unaffected, but can we actually use that to compute the network faster by reusing previous calculations? So I'm going to quickly walk you through how it's done for transformers. So the way you do that is by essentially having a cache of the previous values. So we assume that we already ran the network over the previous paragraph. Now we've changed some of the tokens, like these two. So the light blue rows are the parts of the. You can think of this as like the hidden vectors corresponding to each word in the document, where the light blue values are the ones that are from the cache, and the dark blue are the ones that are changed. First of all, for most of the network, we don't need to look at this entire representation. We can only look at these two rows that have been changed and keep track of where they came from. So this is like the incremental representation. Now, for any kind of operation network, I'm going to show you how I can mostly work with this small representation and occasionally fetch values from the cache to complete the operation. And generally speaking, you can think of like these three kinds of operations in the network. The first kind is the most predominant kind, is what I call paired token operation, which is any kind of operation that's applied at the token level, like the feed-forward part in the transformer network, which operates over a single hidden vector, or the scaling of the values, or the layer norm, and many others. The second kind is element-wise binary operations, when you add two vectors together, and you get that in the residual operation network, and finally there's a self-attention operation. So for the first part, again, this is like the vast majority of operation network are these parts, these operations which are applied per token. So again, this is like the complete representation as you would normally compute in a transformer. Again, these two are the change tokens. And again, because all these operations are applied per token, means that to complete this new representation, I only need to apply the operations over the change token vectors. Right? All the rest can be reused for the cache. So in all the MLPs, layers, everything, you don't need to compute the operation over almost all the previous tokens, only on the change values, which means that the cost of operation effectively scales with the edit distance. There's not much time left, so I'm going to run through this quickly. For the residual connections, it's kind of similar because you have these element-wise additions, but maybe some of the rows are missing, right? Because after the self-attention operation, you might get additional affected tokens, right? After self-attention, again, this is where we apply this rollback operation. Maybe there are other tokens that are now affected by the change. So when you apply the residual connections, maybe you are adding this set of vectors with this set of vectors, but here there's a new token that's affected. So you have to fetch a row from the cache before you add these two together. Now this is your new compressed representation. And finally, again, I'll go through this quickly, for the incremental attention. So attention, if you don't know, is a big name for this operation, which is if you have a query key and value representation for each token, then it's effectively computing this similarity matrix between each query and key. And by normalizing with softmax, which is exponential divided by the sum of exponents, you have a weighted sum of the values according to how much a given key is similar to the query. That's self-attention in a nutshell. And the idea for incremental attention is kind of like how you would update a sum if you change a single value in the sum. So if you have a sum over n values, and one of the values have changed, then that's equivalent to the original sum plus the delta between the two. That's like the basic idea. But if you use softmax, you have these numerical instabilities, which make this kind of incremental computation impractical. So we need to switch the softmax to a softplus normalization. And then, again, I'm going to, just with little time, this is like a diagram of how this incremental attention looks like. It's complex, but it is efficient. I won't go to the details. Let's just skip to the results because of lack of time. So quickly, we've made like 2 small changes to the architecture to support incremental computation. And we simply were able to take the Llama 2 model and adapt it to this new architecture. The changes are that we've changed softmax into a different kind of normalization, which we call soft plus normalization, which doesn't suffer from numerical instabilities. And what you see in this table is that even though we've made this small change, it didn't affect the zero-shot capabilities of the model. So across like these various different tasks, there is some small drop in performance, but it's like less than a point difference. The more interesting thing is that now, using this incremental inference algorithm, you're able to process like document revisions much quicker. So here you guys see these 2 plots. In this plot, what you see is by how much speed up you can get as a function of the fraction of the multiple of how many tokens will change. Now this is like the log of the edit distance. And you see there's this clear correlation. Like I can't rush the complexity analysis, but effectively you can compute things proportional to the edit distance. So this shows you this. This is actually happening in practice in our implementation. Another thing is like what is the speed up respectively to where the token was changed. So the biggest difference is the beginning, because this is the hardest thing for an auto-US network to get to the littlest for an auto-US network to reuse. Well, near the very end, that's why there's little benefit. There's even like a slight overhead to our method, so at the very end you slightly lose if you apply this incremental algorithm. But throughout most of the locations, you get about a 60x improvement. And finally, there's this rollback that we use. So you have to choose like by the epsilon with you roll back the additions. And here you see this the trade-off you have between by how much you get speed up to how much it affects your performance. So this is like the example I showed at the beginning, where you deliberately change the answer, and then you process the edit of the correct one. You see, by So in the very end, you shift like all the activations that are under 0.7 difference, you keep them the same, and you obviously going to have diminished performance. So you start with lambda 2 gets in this one-shot performance squad, you get 67% accuracy. In our model, before any manipulation, there's a small drop to around 64. But in the beginning, there's very little effect. So in most of my graph, I'm using the 0.2, which again, it's about the point difference when we started it. And in that level, you get as much as almost more than 100x speed up when you edit things at the very beginning, or around, on average, around half, if it's like anywhere. But if you are willing to tolerate even more diminishing accuracy, you get even much larger speed up. I mean, at 1000x speed up, it's not that terrible result. It's around 4 points less than what you started at, or 7 from the original number 2. They are still pretty decent results at an amazing speed up. I'm just going to mention that what you propose about using quantization, that's relevant for the quantum case, because yeah, I'm over my time, but just to focus on, there's one thing that I want to show you here. Okay, so in NLP, because language is fuzzy and there's not really one true answer, then making something that's like approximate, that's a reasonable thing to do. But in quantum physics and in most sciences, we're seeking exact answers. And we want very high precision, like in machine learning, like 20% accuracy and you're done for the day. In physics, 99.9%, that's not good enough. So using this approximation of volume bar is simply heuristic, that's not good enough for quantum physics. That will lead to wrong answers. So that's why we actually do use quantization, because that allows you to have results that are in some sense self-consistent. Right? Previously, it depends on the other elements in the batch. This, in this case, the results are independent, which is critical for this system because you have different perturbations of particles. You don't want the energy of the model that you are predicting to be affected by the specific perturbations you're doing. This is where we use quantization. But beyond that difference, all the algorithm is essentially the same. There are some optimizations where because you're operating on, sorry. Yeah. So here you open over a set of large perturbations, so a large batch, there's slightly different combinations you can make, but ultimately you get the same results, you get a large speed up. I'll finish here because I'm out of time. But thank you for the time.